Hello everyone, my name is John Smyth, Ken Dale Travel Award Bursary winner 2020, along with my colleague Joey Aoun. And today I'll be presenting to you on sustainable ventilation in commercial building environments for the new normal. So hopefully a lot of you are aware of what the CIBSE Ken Dale Travel Bursary Award is. As I mentioned, myself and Joey were winners in 2020. I spent the last 2 years working on our projects and are presenting on our report today to you. My initial research proposal was in response to the COVID-19 pandemic, but did expand as time went on over the 2 years to indoor air quality, essentially looking at how we really look at this new look sustainability and reviewing all the guidance that came out in terms of buildings and examining them across these global case studies, which the Ken Dale Award helped me travel to across Singapore, Ireland and Australia, with the goal to kind of reimagine the way ventilation is considered in building design and take advantage of this new research and information in response to the pandemic and for this time in post the pandemic that we are now kind of referring to as the new normal across a lot of publications. So the research aim is to summarize the latest best practice guidance in HVAC building services with focus on ventilation and analyze their impact on the case study buildings. To achieve this, I have 4 main objectives: to classify adequate ventilation and how it will be applied and communicated in commercial building design for the new normal, summarize the latest commercial building HVAC guidance and its operation from global institutions and distill these into actual measures to improve IAQ and building performance for buildings in the new normal, to analyze applicable measures identified on the case study buildings to examine their real world application and results of their implication in commercial building environments, and to present and discuss recommendations to carry forward for future commercial building design. Essentially just provide some background, which is all given in the report, but on a high level, COVID-19 and indoor air quality, there seems to be a cohabitation between the both, and that they had the same root. Where there was COVID-19 or indoor air quality in general, it was about managing the pollution sources to ventilate and to ventilate effectively, which can be additional works of filtration or other things. So if you can eliminate the source, which for COVID could be the sick people from a commercial building and then from any size of pollution inside in an office, but you can also use engineering controls, such as ventilation being a major one inside and in buildings. And indoor air quality, or IAQ as I refer to it a lot, includes more than just CO2 levels and viruses, depending on either way. So just consideration of others, including external things like PMs or internal furnishing emissions, such as VOCs. To just keep things very simple, I simplify it into ventilation into 2 main mechanical ventilation into 2 main ventilation type systems and 3 main ventilation distribution systems. For the main ventilation types, it's dedicated outdoor air supply, which is technically once true fresh air AHU with a heat recovery system and a separate hydronic system, and then a more recirculating type variable air volume system. And then for distribution systems, I have mainly 3 types, in that it's a mixing ventilation system with ceiling supply and exhaust of air, and then it mixes quite well, or technically should. A displacement type ventilation system with air brought in at low level and rises due to buoyancy and is extracted from high level, and then a personal type ventilation system, which is seen a bit more in medical areas now, when air is delivered direct to a person, essentially, and there's can be extracted that way too, but it's hopefully going to be seen a bit more in commercial environments in the future. About ventilation itself, what constitutes ventilation and how much is required? So again, what ventilation actually is, those different between the two, between different standards, whether it's just only outside air or fresh air as we call it, and then how much of it then is required. So some of the different standards are shown there, that they can go as anything from as low as 5.5 liters per second per person up as high as 16 liters per second per person. But which one is right, do we know, or which one is most adequate? That's something we look at further in this report. But essentially, one of these newer standards, including IS 798, brings out a new recommendation levels, and also this categorization of indoor air quality or indoor environmental quality, which I've translated across the IAQ for this research, based on the level of expectation of occupants, with category 1 essentially being very high level, as in requirement nearly for special needs, maybe care homes or something like that. Whereas with category 2 being more medium and normal level or more premium level office use recommendations for supply of fresh air. Category 3 being moderate, fairly typically standard of levels and a good level to be providing. And then category 4 being quite low, which should only be really for short amount of time. And you can see that translates to corresponding predefined and prescribed flow rates there on the right-hand side from BS EN 16798. But you can also just, rather than using predefined values, there is methodology provided that you can calculate it based on the contamination rate and the rate that's been done in it, which we look at it maybe a small bit further in the, you'll see it using the case studies, but it's just to understand that there's more of a performance method of calculating or getting ventilation rates. About ventilation, another important fact, and I will reference it a lot and mention it, is ventilation effectiveness, which essentially describes the performance of a ventilation system in removing pollutants from the occupied zone. So this table on the left-hand side here is just taken from ASHRAE. It's about ventilation effectiveness, and just details I show is about the different distribution types, whether it's a mixed air system, we can have anything from about 0.5 is up as high as 1, versus a stratified air type system, which is displacement type, which can be anything from 1 up to 1.5, and then personalized, which can be anything from 1.2 up to 1.5. And it also just shows maybe the different things that have an effect on ventilation effectiveness as well, including supply temperatures, the position and location of intakes, and supply and exhaust, the velocity of air, this kind of thing, which is represented a bit more simply graphically there on the right hand side. We go into ventilation effectiveness a small bit more in the report if you want to have a further look. Just in terms of filtration and air cleaning, just as I mentioned earlier about ventilation not being an outdoor air, not being the only method to remove contaminants. So is it ventilation then? And this comes back to a bit more about this effective ventilation or effectively ventilating. So essentially ventilation as an outdoor air is definitely a very good way to get rid of many of the different pollutions we're considering, but mechanical filtration and including gas molecule filtration can definitely help in the removal of different areas. And there's also disinfection and purification techniques such as ionization and UV light. But as we show here in this report and this graph that shows it quite well actually from Cosentini, that essentially a well-designed mechanical filtration type system, with maybe gaseous if you do need it for odors, but there's a consideration for that also in the report if you want to see a recommendation as to when it might be needed, is actually quite effective at removing pollution without maybe the need for UV or for one of these other air cleaning technologies, but we discussed that a small bit more in the guidance measures. So in terms of filtration, though, there is a requirement really, because it can be spread across different standards and how it's specified, and then how effective is it if you are going to be considering in calculations. So a lot of work was done in the report there on maybe harmonizing that and what the different standards relate to, which is shown here on the graph on the right-hand side, which generally I do refer to them inside using the typical EN 779 ratings or MERV rating, especially if I'm looking at LEED, but just as a good reference there. So the HVAC best practice guidance, which was a main part of my research, which I spent doing during a long hours of COVID time. But there was so much guidance and best practice docs, and it was constantly updating. I'm sure I'm even a small bit behind now at this stage, and I didn't get to cover everything, but I did pretty much look at least the 5 global recognized HVAC industry expert bodies covering a range of geographies and climates to get their main input, which was brought in from a lot of different areas. And in general, there's consensus that these measures are beneficial, but the specifics do vary. This is included inside the report where I just go across the 5 different groups, which is ASHRAE, ARI, CIBSE, RIVA, and ISTRA, which is the Indian version. And look, it's inside the report, so you don't need to look at it now, but all the different areas mainly try to pick it out between the standards and a summary of each. But essentially, I do go further than even inside the report, and here just for ease is to go and to summarize even further and maybe condense it or distill it into even easier categories that can be tackled inside of the case studies. But in summary, in general, DOS or dedicated outdoor air supply is preferred, but I do believe recirculation type with suitable air cleaning is acceptable. That's seen a lot inside in American standards. But one point I do want to definitely recommend is that greater ventilation effectiveness has greater sustainability, and this is this new look of sustainability, including indoor air quality and energy, because you can either improve at the greater ventilation effectiveness at the same airflow rate, you can improve indoor air quality, or you can have the same indoor air quality at lower energy with this effective ventilation. Ventilation rate and operation, look, adequate ventilation recommended, but what is it? We look at that a small bit more as we go forward in the next page and on the next 2 slides or so. And that only thing I do maybe differ small with the guidance is that well-designed DCV units should operate really as normal, I just had an example in case study building where they were pumping full fresh air at 100% into a room that wasn't occupied. But once it's well designed and it's working well, I think it should just be used the way it is. And then purge ventilation, which is just essentially between occupancies, rather than doing it, just leaving it on for a certain amount of time or different levels, just achieve 3 air changes per hour to remove about 95% contaminant removal based on looking at different calculations. But again, referenced in the report. Temperature and humidity, keep it in the recommended comfort ranges for your different climates, should be fine, doesn't have a major effect within the comfort range zones anyway. And then indoor air quality monitoring. CO2 is great as an IAQ indicator, but going forward, a more holistic view of indoor air quality is pretty much recommended between, definitely look at maybe some TVOCs and something external based, such as PMs or NOx, or particulate matter for PMs. Air filtration and air cleaning, as I mentioned, mechanical filtration is probably the best, but based on my research, that filters MERV 13 to 14, rather than going all the way up to HEPA, which is F7, F8, is recommended. That it's the best value balancing pollution removal and energy penalty. UV dominant air cleaning technologies are only really recommended adjacent to cooling coils, like in warm, humid climates where they can have a benefit in reducing coil fouling and improving sustainability while doing the extra deactivation work. But technical filtration should be enough to achieve what we're looking for in air cleaning. Local air cleaning can be a help inside in rooms where they have maybe a bit more effective, and they can help achieve greater effective air changes, which can help with resilience or pollution removal if required. And finally, mechanical ventilation heat recovery, there's actually a lot of guidance out there on that. Essentially, though, it really shouldn't be bypassed, which is kind of, I think everyone has come to that kind of conclusion now, because it's important for indoor air quality, indoor environmental quality and temperature control in general, and just to follow the recommended guidance on fan positions and pressure regimes, which is then a bit more in the report. But even with all this and all the different guidance, and there's a lot of similarities across, I do recommend that HVAC measures should be assessed on a case-by-case basis, and particularly the effectiveness of each measure, the cost and its implementation, which we'll see a bit more in the case studies. So I looked as part of this research as well at several building certification systems, namely WELL, LEED, BREEAM, NABERS, and the Immune Building Standard. In general, certification costs for these standards is actually a barrier to being employed or even looked at for a lot of projects. But in general, the information for them is free and quite accessible. And therefore, I'm recommending that it's considered, particularly with, say, the WELL Building Standard and their air measures, to be considered in part of the design, and to be the knowledge of them to be shared amongst design engineers, especially at early stages, to understand the implications of what they can and cannot achieve. Not every measure is always applicable, as I point out inside in the report. LEED itself has some good credits on low emitting materials and this management of pollution sources before we even consider ventilation, so that we can achieve an indoor air quality. So I do recommend that those be considered as well and just to be learned about. And while BREEAM has a very good indoor air quality plan credit, which definitely helps with the communication at early stage about ventilation requirement, indoor air quality category, really are you trying to achieve? What strategy are you going for? And it's ventilation effectiveness and indoor air quality monitoring. And then pollution management, again, as we mentioned, is what way are we going to tackle this, which I think I refer to do later, but CTTM 64, I hope I'm getting that one right, definitely has some great recommendations towards that house and the management of pollution sources. The general immune standard wasn't really applicable, mainly a lot of medical stuff. And then NABERS, which was actually big enough now in Australia as my case studies. I do expect to see it more in the future, but just maybe not applicable to what I was looking at now. So, as I mentioned, adequate ventilation, widely recommended, but no real consensus on the definition of what is this adequate rate or how it is demonstrated in operation. So that's something I try to tackle or to classify inside this report, where basing it pretty much off this BS EN 16798, I provide an updated categorization of adequate indoor air quality using their categories based on the level of expectation of occupants, which then translates into predefined ventilation rates, which are preferred by us engineers. But that doesn't really consider all the indoor air quality characteristics. ASHRAE 62.1 has an indoor air quality type procedure, which is performance-based and allows the inclusion of ventilation systems, performance metrics, and the use of air cleaning. However, it does require a good bit of calculations and consideration of mass balance and validation as you go into later design. So as a result, I propose a mixed methodology approach, which provides the comfort of these predefined values, but with a ventilation performance characteristics in the form of ventilation effectiveness, which we discussed briefly earlier. As part of this, then there's the classification of ventilation and its different rates. With on the left-hand side, you'll see there for a typical low-polluting building, which look, there's guidance given as to what low-polluting is, but it's not perfect. Again, it's seen inside the report. And then this very low-polluting building, which essentially I have gone to the point of saying that anything that is very, very low-polluting building is essentially considered the management of pollution sources within the building, whether that be through well credits or lead credits or through CIBSE guidance, but that they've been considered, and then you would be a very low polluting building, which I hope in the future will be nearly all buildings, especially in this new normal. And that the ventilation rates here don't even have to be used as the reference or the exact value. You can still use a CIBSE recommendation value, but you can then classify it against these proposed categories and use that as a communication point between the client and maybe different projects. This can be further enhanced with benchmarking using this adapted method too, which is from that same standard limit values for concentration, where you can calculate based on the flow rates that you are, airflow rates or the ventilation rates you're supplying, what the CO2 levels would be based on an assumed number of occupants which you're using at that stage. And then these can actually be compared to this table below, which will give you a classification which should match based on the work that I've done, the table be previous. But these calculated values can be used to validate achievement in design for this category, IAQ category target with ventilation rates and effectiveness, with significant variations in site measured CO2 rates highlighting any potential issues compared to what you had in design. And this is something we see a bit more in one of the case studies. And just however, CO2 cannot account, because CO2 was the category that we used, or the contamination or pollution that we used. You can try and use others, but it's very common and measurable to use. It cannot account for HVAC-based mitigation strategies, but ASHRAE 62.1 does have an effective air change rate metric that accounts for this, particularly in recirculated air volumes, where you are getting a benefit of this recirculated or a lot higher levels of air and the air cleaning efficiencies. So using this updated, this mechanical filtration calculations that we referenced earlier, you can use this methodology to make sure that you're including it inside in your calculation for effective air change rates. And I have a recommendation essentially based on American CDC rates and what 3 and versus 6 air changes might achieve as to what category levels recommendations are to be included in that. And you'll see a comparison versus the flow rates, if they're provided, how close you are to achieving these air change rates. Anything that is quite high, if you want to achieve higher air change rates, you're able to use local ventilation, which might be just simple air cleaners to help try and achieve it within the room, rather than going all the way and increasing the size of AHU and ducts and other considerations. So based on everything I've said here, the case study analysis, the important part of what I did inside the case study was my 5 global case study buildings analysing 2 main subjects: ventilation adequacy, which we just discussed, analysis of building ventilation design adequacy in terms of desired indoor air quality rates using this proposed methodology, and then the HVAC measures and the analysis of the needs and sustainability. So as I mentioned, at the Arup office and NUS SDE4 in Singapore, I also have 3 case study buildings in Melbourne, Australia, Sydney, Australia, and Brisbane, Australia, which were originally highlighted as actual buildings here, but we did just anonymize them just for the benefit of the client going forward on their request. So case study 1, I'll try and go through these quite quickly. There's a lot of information within the reports, but this was the Arup office in Cork, a commercial office building that had a well gold standard fit out. This is a summary of the HVAC system with table on the left and trying to do a graphic representation on the right, but it's a dedicated outdoor air system with about 3 air changes, different occupancy rates, which based on the fit out versus design, we had a lower occupancy rate that improved things in terms of air quality, and that we have a mixing type ventilation system with an EV of what we expect to be about 1. So I did ventilation analysis then based on the design. Just looking at design values, which originally it was core and shell, it was 15 litres per second per person at a 7.5 meters squared per person density assumed. Arup actually ended up increasing that to about 10 meters squared per person, but we still had the same amount of supply air from the core and shell design. So we ended up just having a lot higher flow per person inside. So we had a good category air. But then, and we expected, so based on this supply rate, that we'd have a supply air flow rate of maybe, or a CO2 level inside the room based on design of 640 ppm or thereabouts. Then inside an operational analysis, which this is CO2 monitoring values in 2020 in the Cork office. And based on the calculations, we were getting values up, not terrible, but they were a lot higher than what we were expecting. That could reach as high as 800 ppm quite often. And that didn't make sense to us. So that was quite a deviation from what we were expecting, which we said we'd go into more detail. Because if we did inside this calculation below, which might be a bit hard to see, but again, in the report, it was just using this adapted method 2 calculation to understand, okay, if this is the value what we're getting, what are we saying? So the ventilation effectiveness value based on this is coming out at around 0.6 rather than the 1 really that we were expecting or wanting to see, which means maybe there's short circuiting or maybe we're not getting the supply of air that we were expecting. So this then required further investigation, which I look at inside the measures a bit more. Ventilation effectiveness, we'll see what we have in design versus actual, which is a bit lower as well than what we're expecting. It's down to category 3 based on even just what we're getting through with the ventilation effectiveness value of 0.6, we should be getting higher air changes. And if that can be improved in any way, that's something we look again at the measures. So with these HVAC measures then, this is based on, as I mentioned earlier, there's more detail again inside in the report, but essentially the main measures are around ventilation rate and its operation. So as you mentioned, we were supposed to have about at least 21 litres per second per person or 2 litres per second per metre squared based on the level of design, but we weren't achieving that based on the analysis that we did here. So what we did do though is we did, based on a bunch of other improvements we analysed that go into a bit more, especially found where the air was actually recirculating or leaking in this case up in the thermal AHU and thermal wheel in the AHU, and we're able to reconfigure. So even though we did bring the supply air rate down to 50 litres per second in the future, we were able to maintain indoor air quality to the same level, even though we were reducing the ventilation rates because it was coming in more effective. We weren't having this recirculation or loss of air. Also recommended just increased air change rates between occupancies nightly. There's not a major capital cost or increase in energy consumption based on that. They kind of do it anyway. And then we also added additional fan speed control for full occupancy, medium occupancy, and low occupancy. It was a constant air volume system. I don't know if I mentioned that earlier previously, but just to work on the occupancy levels with the building manager because it is a tenant-based system. So that's just able to improve our sustainability while also achieving the indoor air quality we're aiming for. So, in terms of air filtration and air cleaning, we do have Plenum FCUs, which could actually help improve our effective air change rates if we added additional filtration levels to them to help with the local air filtration, because it does take back in some recirculation air, although not a lot, but it's not a full fresh air because it does come up through the plenum. And then we just were able to upgrade the return air filter to a higher level within the HU itself, just on any possible recirculation that might go through the thermal wheel that it is cleared out. And it also helped with the pressure reconfiguration of the AHU wheel so that we did not have any bypass or thermal or air leakage in the wrong direction in the zone. Indoor air quality monitoring, we just added some additional indoor air quality monitoring that has actually been installed around in the offices now. And then just on the MPHR, which is the important point here inside an Arup, where once we investigated that our ventilation effectiveness, our values weren't as what we expected, we worked back up the ducts. It wasn't recirculating within the space, back up into the AHU, and we did find, I'll show it here. Yeah, we did find a significant gap inside in the thermal wheel, and that did have air coming back. And with the way that our wheel was operating, we had a gap coming from recirculated air back into the supply air, which drastically affected our ventilation, our supply, and why we had higher CO2 rates, because we weren't getting that fresh air levels that we were expecting. So we had to do some upgrades around this. And that was included fan speed control, updating the filtration, and improving the sealing around these thermal wheels, so that as we then going forward, we're able to supply a lower amount of air rather than higher than 21, but we could work at that medium for the occupancy that we had at 15 litres per second. We were achieving we're still achieving better CO2 or indoor air quality rates. These are the results from monitoring there in 2022. You'll see that the ventilation rates, there were standards. Occupancy rates do vary a bit inside in the office, but we aren't reaching the same levels, especially not as consistent as going forward. But we were even at a lower air supply rate here than we originally had, based on our control of airflow rates inside in the office. So overall, this was a good update and a good increase inside in the Arup office, and something we spent a lot of time working on. So case study 2, this was in National University in Singapore. It's SDE4 building, which is a fantastic building and great to visit. It was first net zero building, energy building in Singapore, and world's first university building to attain WELL certified gold. Again, this building has a few different systems really going on, but we focus, I suppose, on rather than the outdoor naturally ventilated spaces, either the hybrid tempered spaces or the full AC spaces, anything with essentially mechanical ventilation. But this building was pretty well designed as it is already, but we had specific interest in how the ceiling fans, which they were using for higher related thermal temperature control, which is explained a lot in the report, but better comfort at higher temperatures and how they were maybe affecting ventilation effectiveness or indoor air quality. Again, going through the design, everything was at a very good level, and as to be expected, it's a well-designed, good building, achieving at least category 2 design, which is premium space, particularly for an education facility. When I went measuring on the day, it was actually quite a bit less than again, occupancy levels it was around summer holiday time, COVID measures and mechanically ventilated zones were only partly occupied, so a lower CO2 level is kind of expected. It's not the same concern that we were getting from, I suppose, higher CO2 levels inside in the space in the Arup office, but if this was very low and I didn't have a reason as to why, I'd also be asking questions as to the measurement, even calibration, or maybe what is going on inside the space. You might have a lot of internal room air leakage, infiltration maybe into the room, so different concern, but maybe not a major in this case, because we had different occupancy rates based on what I was able to work with at the time when we did travel. The effective air change rates were also quite good in the same category as to be expected at the premium level. There was no need for additional indoor air cleaners. They had supply of fresh air in mechanically. It was once through that would leak out into other rooms as necessary, and good level of filtration. So based on this, there was not a lot of measures obviously to be implemented inside in the space. The main thing that we do talk about is the high-level ceiling fans and their mixing ventilation system, because they did assume with an EV of about 1 in effective ventilation. It is recommended, I suppose, to maybe have a better look at this with CFD analysis and stuff, but there was actually some research done, as I presented slide in the report, which looks at it and actually might help in the improvement of ventilation effectiveness and the removal of pollution particles from this occupied or this breathing zone, particularly in terms of maybe virus particles is what was looked at. And it might also benefit from purging between occupancies, which wasn't noticeable or within the control strategy or at the time. But again, the rooms I were in and who we were talking to, they can be mainly quite consistently occupied with long enough hours, but then overnight there is some allowance for ventilation before they occupied again. And then indoor air quality monitoring could be displayed. They did actually have some sensors around, but maybe in the more occupied rooms there could be improvement there. So essentially, as I mentioned, great facility, and there was a lot of study done on the effects of ceiling fans on airborne transmission, which was actually quite interesting and a very good read. I do recommend it as referenced within the report. So building A, so case study 3 is building A in the Melbourne office, which again, a few details related to it, a Neighbours 5 energy building, and a premium type office space that was well designed again. I do have some details as to the schematic and what the graphical information of the HVAC system that was included in it. In this case, it was a recirculating type VAV system, variable air volume system, with an outside air provision of about 8 litres per second per person, but a good level of filtration and a high level of recirculation, which helped with higher air change rates, because 8 litres per second was the outdoor air provision, not the total air provision. So there was a lot of other air being supplied as part of this recirculation of air into the system. Again, mixing type ventilation system with EV of about 1. So again, looking at the ventilation analysis, taking what I had to on the face of it, I didn't have any knowledge or information to suggest that it was a very low building to look well standards, or maybe didn't have the information, even though it was well considered and they looked like they were managing pollution. I just went with the higher ventilation standard. So even based on that, they are it is on design category 3. If you only consider outdoor air ventilation, as we go on through, we'll see and we understand with air change rates and other things that's probably not very representative of the actual building. Nonetheless, based on the methodology that I'm proposing, that might need to be altered a small bit. It is coming down at a category 3 building and with a ppm rate of about 1,000, which isn't terrible. It's not a bad space, but that is category 3. Then when it came to operational analysis, as I said, things were better. So 7:60 p.m., which is actually what was measured in the space, which is a lot less than the category. Again, not fully occupied. There's work from home practices and other things that were going there. So lower CO2 kind of was expected. I did recalculate then based on this at the lower ventilation rate, which because of this, the lower thing, and the lower occupancy. And it did give a similar enough type results or better results to be more along the lines of what was expected. But essentially, I think, there might be some rejigging of my analysis or everything, how it is, or at least considered wholly, particularly with air change rates as to how it's done, particularly for recirculation type VAV systems, because it might not be truly representative of just looking at outside air and its provision as part of a ventilation standard. But again, as this effective air change rate is mentioned, that's a lot higher, and this is actually up to a category 2 standard than this category 3 standard, because you have this beneficial effect of this filtered recirculated air also improving the air change rate and the pollution removal inside the room, which will definitely help with air quality. So look, based on this, again, measures across the building, we had recirculation variable air system. Might be worth looking at how it might work in terms of a wildfire. And in this case, they actually did have a standard with this recirculation type system to go full recirculation for a period of time, just while this public health emergency was on, and then they could refer back to it, which was useful and definitely helped with building resilience. It is recommended, look, based on what I'm working at so far, that the 8 litres per second could be increased. They are actually able to increase the amount of supply air and outside air based on we're using the damper system up to a higher level, based on what we're looking at between about 10.5 and 14 litres per second, based on these BSEN standards that we referenced, or my methodology proposed throughout. And look, air purging and modulation control are recommended for the outdoor air rates, just to help with indoor air quality, but also on the sustainability front to minimise unnecessary energy use while achieving this indoor air quality target that has been agreed with the client and with the building operators. Again, indoor air quality monitoring, although some of it was installed within the BMS, that it can be brought into dashboards and other areas in the space so that people have an awareness and can increase their own understanding of indoor air quality and what they can do to improve it too. So again, Building A looks at a recirculation type system, considering external public health emergencies, particularly wildfire smoke in design operation. And the main impact one is to increase the ventilation air to a higher level based on the research methodology. Even though we are achieving quite well indoor air quality based on effective air change rates, just on the research models to be consistent, it could be increased up to this level just to ensure there is that fresh air volume for that's recommended for the occupants. Okay, so case study Building B was in Sydney. Look at a top quality premium office building again. This time though, it was a dedicated outdoor air supply unit with just fresh air running through and a separate exhaust. No heat recovery is probably one of the main things. And again, high level distribution with an effectiveness of 1. This actually building was very well designed from the off. Great, very close to being a category 1 type building, and very low CO2 levels expected. Those were also measured, and even at that, there was they're a bit lower because there was lower occupancy, again, just based on the work from home practices and what were going on. So it was even a bit lower than to be expected. But this building then even had high air change rates, just based on the high amount of air that even as a direct system that they were involving. So there was no need for local air ventilation. And so really it did not have a lot of measures for this building. It was a very well designed building. It looked great to see it and how well it was run. And they were, even at this one, they were working on achieving a well standard at the time for in operation. So possibility to improve purge ventilation to 3 air changes per hour. They just weren't able to verify really that at the time, and never did find it afterwards. But I'm sure they've probably implemented it now based on the feedback that I've worked with the client on this. And then there is a possibility to improve air filtration. Look, investigate the possibility of maybe including some idea for HEPA filters or some higher possible grade for temporary installation in terms of external public health emergency measures, especially look wildfires, which Sydney was a bit succumbed to in the past few years, even though this building themselves said they weren't really terribly affected by it. And that it just might be worth considering because they don't have a recirculation type option even for a short amount of time. And it can also help positive pressure of the building, so there's no little infiltration. And again, indoor air quality monitoring can maybe be improved just to increase awareness. And just look, it doesn't seem like it was a big issue on sustainability. Sydney has quite a nice climate for it, but there was no MVHR. So even a runaround type coil system might help and reduce some of the energy loads, but that would require further investigation, which I'm sure us and the Arup team offered to help them with as well if they want in the future. So look, in general, great building, not a lot of measures, maybe a runaround coil, and that just for estimated fire smoke removal. Fire smoke is actually even smaller particle size. So even though I had these filtration levels earlier that we worked quite hard on, it's just even considered that why I recommended maybe HEPA rather than the usual 13, 14, because the standards are, the particles are a lot lower. So you need maybe a better one for better efficiency. And if it's only for a short amount of time, it shouldn't have a major effect on sustainability. There won't be a forest fire for all time of the year, for example. So hence the recommendation. Case study building 5, then our building C is in Brisbane, which is a slightly warmer climate up more northern in Australia, but look East Australia, sorry. Again, HVAC system is very similar, I suppose, to the first one, but in a new location in that it is recirculation, VAV type system, high level supply with effectiveness of about 8 litres per second per person, and look similar operation and at different levels. Again, so since it's similar to the first one, root and recirculation type, the design categorization doesn't look represented really truly that well with a category 3, which is not bad. Look, a standard enough office, but these are premium type office spaces. So when I discussed this with the clients or with the building owner operator, they were maybe a small bit disappointed on with the level of what the design level was too, which look I can maybe understand, but maybe I need to update my color coding here because yellow shouldn't mean a warning. It's more like it is still pretty okay, but it's maybe not, I suppose, at this higher levels that can be achieved. Again, so then, okay, this building actually was maybe, this one had one of the lowest occupancies of all the buildings, but again, and the air rate was very low. The CO2 measure was very low due to mainly work from home practices. There was no really there, but also they actually had a DCV strategy, which would have reduced the airflow rate based on this CO2 level stuff going back, but that was actually disabled based on guidance they'd received. So they were just pumping full air into the room, which not a lot of people in there, hence a very low CO2 level. As a result, they were also putting in a lot of air into the space, particularly even though they had percentages and with the VAV, so they were using some recirculation, not full outside air, but they had a very high air change rate inside there, which they could even reduce based on not a lot of people in there. But so it's even category 1, which is a lot different from the category 3 that we first identified. So really one of the highest level measures, I think, again in there, this 8 litres per second could be increased to 10.5 or 14, depending on what they can achieve and the pollution management of sources, that kind of thing, purging, and also I do recommend that they re-enable the AHU CO2 demand control, because this will improve IAQ for the levels to what is required on the standard, but then at very small capital cost, but really help with operational cost. And then look, there's just filtration there. There's an opportunity to improve the filtration levels up to a higher level, and that even if filtration alone isn't fully necessary, or they can even use those filters, and maybe if they want to improve resilience, they can actually add UVC. I would recommend it more in this area because warmer climates, they literally only just had cooling it's allowed for, and that the cooling coil in this warm, humid climate is running quite often. So there was a potential for fouling, which the UVC adjacent to it can actually help with and improve overall sustainability. So there was maybe a further investigation because it's hard enough to implement inside here, but I know that's something Arup actually are looking at for them. And look, and improved indoor air quality monitoring could be a benefit. So look, recirculation type building, main recommendation about the increase in airflow rates, just to align with the proposed standard methodology that might need to be updated, but proposed methodology in this research. And look, that while filtration and ACH may be acceptable, this UVC may help improve the overall sustainability by eliminating coil fouling or reducing coil fouling to help with overall sustainability and indoor air quality at the same time. So briefly and quickly, apologies for how long I've gone, but the main conclusions really is that sustainability now includes indoor air quality, and that is just more than just CO2. And while there is no main consensus on adequate ventilation, I have hopefully proposed a methodology that how it can be kind of classified against and adapted these BSEN standards that I proposed, allowing for system effective ventilation so that it can be considered as distribution and these performance characteristics included. Mechanical filtration is the best air cleaning technology to improve indoor air quality and building resilience and this effective air change rate. But again, UVC does have benefits in warm, humid climates. This new normal for HVAC guidance varies between the different standards, but in general it is beneficial. However, usually only considers COVID, especially at this early stage, and does not always align with my recommendations then that I propose in here. That's why there's some differences. Building certification standards and their measures are usually building certification itself is expensive, but the IAQ measures are a valuable and accessible resource. So selected well, BREEAM and LEED measures I think should be considered in design based on my research. Public health emergencies, so COVID-19 for internal and wildfires for external consideration, I do think is needed. And that's not just in Australia, as I point out. It can be across Europe. We've had wildfires and around Spain and stuff recently. So understanding how to act in terms of an emergency thing like this should be good with an emergency type plan, which is actually a credit, I believe, in Slide Well, that can be looked at as well, and a strategy for that. And look, not all guidance measures are required or suitable for all projects. Assess on the impact of sustainability on a case-by-case basis. Just to review and to go back over, adequate ventilation is classification and specification, because this was the main objective. That it can be classified at early stage using the proposed updated IAQ categories, and then validated in operation stage using the adapted Meta 2 formula with actual occupant levels known, so that you can use the calculated CO2 level to compare it against and then highlight if there's any major differences. I think source pollution or pollution source control is key. If it's well implemented, it can reduce ventilation requirements. CIBSE TM 64, got it right earlier, is a recommended guidance. Everyone should read it on that as to how to minimize that, because then you can achieve the same indoor air quality that was what we're all trying to achieve with ventilation, but maybe a more sustainable rate on a lower energy front. And to achieve greater building resilience using effective air change rates based on desired indoor air quality. So look as to what you're trying to achieve and how resilient you want your building to be in terms of the pollution sources, whether they be internal or not, is something that can be again discussed at early stages. So overall, I think an updated approach to ventilation design in this future is kind of recommended, take into account the updated approach to ventilation specification and classification and the additional HVAC measures as detailed above. This approach actually can be assisted by CIBSE TM 61 and all the way to 64. They have things that use, I think, TM 62 or 63, talks about classification or validation of even energy simulations, which can be nearly adapted to what we're working on here for measuring indoor air quality. But essentially, it is about the early stages of defining targets for indoor air quality, this categorization or classification, including this all in this plan, looking at ventilation distribution and identifying its effectiveness and how you might work with that and sensitive areas. And then defining these volumes, doing the calculations and specifying low, minimized pollution inside in the construction stage, and specifying it in it's not only the systems, but in while you're doing it in construction, and then to in post-occupancy evaluation to commission things right and to measure and check then against the design that we've now included and that make sure everything that is working well, which isn't a major variation. I'm sure a lot of people are doing it, but it is a recommended updated approach, at least to maybe some of the approaches we had in Arup. So that is the end of my presentation. I'd like to thank you all for listening, and I'll happily take any questions by email in this case. Well, thank you.